Hello timing folks, Rashid here. Thank you so much for joining. This is second video on timing constraints. Okay, I was reading comments and questions that came in YouTube and LinkedIn, and I put these 6 bullets where I feel the questions are around. So questions are not directly like this, but I just created the 6 categories where different kind of questions from basics to advanced you can put under these. Okay, so the first one is, what are timing constraints? Why those are required? So a lot of basic stuffs explaining that comes into this category. And then how you create them and apply them, and then when to apply them, how to verify them, whether start applying them at block first or at the top first. So yeah, I think so far all the questions that you have in your mind fall into one of these. And if you have not asked me question yet, please ask them, because that really helps me create this curriculum more aligned with what your questions are or what you think of it. Okay. Otherwise, I create with my own kind of mind, and that may not be the same as yours, right? So I really want to extract your brains and figure out what is the biggest pain point here. So don't be shy. Even in the comments of this video or the previous video, please share your comments. I read all the comments and I replied them, and for some reason they didn't seem to be updated. But anyway, I will look into it, but I will read all of those in a day or two. So don't be shy. Tell me what you think is the best way. I might not use that, but I will read those and I will consider that input, and I will judge. I have to look at from different people angles, right? So, but you can totally look from your angle and tell me what you think is best for you. And I will promise I will definitely go over it and will seriously think about it. Okay, so here is the way I was thinking how I can cover all this. There are a few different ways I can do it, but I want it to be a little different and more practical as well. Okay. Give you theory, but also give you how in a modern SOC, how sign-off teams, how those chips which are actually created with which are produced, and those SOCs are working in the field, and companies are making money based on those, how those chips are implemented, and especially in the context of this series, how those are timed and how timing constraints are created at what stage. So I created this sample SOC. I'm calling it OSoC 10. I call my other SOC. So in case you don't know, I have another series, a parallel series going on right now, where I started with the architecture of RISC-V RV32i, and I'm building an SOC, not just CPU, but an SOC. And that SOC is very simple for industrial application. And that is, compared to this one, that other one is tiny. But those people who are interested in learning architecture and microarchitecture and then implementation and then physical design, I will do a physical design of that too. And I will start all the flows, all the timing constraints from scratch. But that other SOC is going to be flat. That is tiny compared to this one. And that other one will, I think what will have maybe 3, 4, 5, 6,000 or maybe up to 10,000 instances maximum. It won't have more than that. Plus, of course, memories and all that. But this guy that I created, I plan to do a top level where your entire design is about 20 million. Still is smaller compared to some of the modern SoC I'm seeing in the industry right now. But it is big enough that we cannot well, maybe we can, but we will not run a flat everything. We will not load all the in the physical design. Okay, so think of this in physical design when do synthesis, place and route. This is pretty big. So even these days, the tools have become very capable. They can take huge design, and then runtimes have improved a lot. Memory has improved a lot, but still, if you take it, it's gonna take a long time. A 20 million instance like this during synthesis, during placement, during CTS, during routing. And if something happens in one of the steps or stages, and you have to go back, it's gonna take a little while before you have another out of database. So in order to do that, what you do is you divide and conquer. You divide it into a number of smaller blocks, more manageable, where in 2 to 3 days you can take a synthesis, an RTL, synthesize, place and route, go all the way to route up and do a timing at block level. Okay, so 2 to 3 days, and maybe some of the blocks you can be longer, but maximum a week. You can go from synthesis to route up for fill in 1 week. Mean one iteration can take 1 week, but most of the blocks here will have 2 to 3 days iteration time. And that is manageable. That means you can respin each one of these on its own without worrying about something else. If it's a USB RDL changer, USB controller and all that, you just respin this guy, not everything else. And eventually at the top level, it's like a Lego building, right? You have different Lego pieces and you put them together, and each one of them is verified on its own. The challenge, of course, comes when you put them together. If there is any communication between any blocks, is that also clean or not? And that's something you have to verify at the top, but you can design it such a way that when you put those pieces together, you don't have any problem. No layout problem, no timing problem. Okay, so what we do is this video and maybe next video, we go over this design. So I don't have an RTL of this one. So, but I can give you, because I did SSEs like these, I managed those ones from start to end, and I led teams, managed teams to do complete tapeout. So at least I can tell you which stages or what stages we have gone through or we will go through, and what kind of challenges I've seen or you will see typically on this. And this will be, I think, a good example. And through this one, we can answer all of your questions here. Where you start a block, top, how to verify constraints, when to apply them, how to create, and all that, right? So kind of this is our design. This is an RTL is given to us. We have a physical design team that is executing this, and you and me are the timing team. And maybe some of you are also the physical implementation. So I think we do something like this. In this video, I kind of imagine some of the block sizes for this one, and based on that, overall has become 20 million instances. And then I also assume certain clocks there, and each one will have some internal clocks, which only the logic within that partition of block runs on that clock, but they on certain clocks, these will be communicating with each other. Majority of the 99% of the design is synchronous, so we will definitely use clock. Maybe some instances of asynchronous timing are there, which we can also discuss. Okay, what could be the potential asynchronous timing in some of the blocks. So, and then after that, we will need to build a team. Okay, how many partitions we have, how many timing people we need, and how many top clock, and blah, 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 and all that. Okay, so I think this exercise, in my point of view, will help us adopt a more practical approach as opposed to just going over the theory. And hopefully that will prepare you well for any interviews, as well as if you have already in a job, it will help you broaden your vision, and you can see things from a top level, because most of the time you go into some block or even full chip timing and you have a very narrow vision or things, because maybe you haven't done a tape out, or even if you did it, you were sitting at a very low level or maybe inside a fire somewhere. So at least this will help you see things from the top level. Okay, so another kind of a background video. But then we are gradually getting there onto the timing constraints. But I feel it's important that I explain these concepts or these things to you first. Okay, all right. I will see you pretty soon, and I'm really looking forward to this playlist. I think that will be total fun. Bye.